Okay, so if you guys haven't done this with me before, this is something that I started before my last exam with my classes, so welcome if you're in Miss Belden's class. But this is basically just a way for you guys to get some extra review. You can interact with me, so send me questions on Remind or in the live chat. On the live chat, you do need to be logged into your YouTube account, so if you don't have one, just use Remind. This will be available on my YouTube channel after this, so if you need to leave or if you didn't have time to watch before, you'll be able to watch it later too. But the nice thing about live is you can ask me questions as we're going. Your test for my class is Wednesday. For Miss Belden's class, I know is Thursday, so it is coming soon. You should have started your reviews hopefully already, but if not, this will give you a little bit of a head start on it. The next review session I'm going to do is Tuesday night at 7, so that'll be a nice chance for you to review right before the test, and we'll do more applications then. So these are your learning targets for this unit. A lot of these are very skills-based, and they're things that you're going to have to know how to do for any variety of situations, but a lot of them are just integration techniques. So finding general antiderivatives and particular solutions, knowing that you always need to have your plus C is important, and then finding antiderivatives of every different type of function, which we're going to go through in a second, and those different special types of antidifferentiation, so substitution, using long division, using completing the square, are all going to be important aspects. There will be some just straight up, can you take an antiderivative type of problems? There will be a lot of application problems. There will be slope fields. So it's not a lot of content on this test, but there are a lot of small places for you to get stuck. So you want to make sure you're very clear on your skills so that the applications you'll be able to handle. So we're just going to start with the antiderivatives that I need you guys to know. These are them. And based on your 5s quizzes, some of us know them super well, some of us don't. So these I would, screenshot this. I have given this to you in class. I am sure Miss Belden has given this to you in class, but these are the ones you need to know. So your general derivatives that you need to know, and you can't integrate unless you know these derivatives, right? Your general derivatives, anytime you see a variable to a power, we're talking power rule. So you would bring your power down to the front and then multiply by the variable to that power minus 1. So for example, x cubed, the derivative is 3x squared, okay? Derivative of sine is cos. Derivative of cos is negative sine. Remember that anytime your function starts with a c, its derivative will be negative for trig functions. Derivative of tangent is secant squared. Okay, oft forgotten, but very important. Derivative of tan is secant squared. Derivative of cotan then, and these are going to kind of be linked together, is negative cosecant squared. Okay, those are related, right? Tan, cotan, sine, cosine. And then secant and cosecant are related. So derivative of secant is secant x tangent x. And derivative of cosecant x is negative cosecant x cotangent x. So again, patterns to look for. Your cofunctions go together, and anything with a c as your starting function will have a negative derivative. Okay, good. E to the x, everybody's favorite derivative. Derivative of e to the x is e to the x. Does not change. If you are doing chain rule, you're going to have to think about this a little bit more, but otherwise, just e to the x. A to the x is a to the x ln a. It's not one that you see often, but it does come up occasionally. Make sure that you know that. Ln of x is 1 over x. Okay, ln of x is 1 over x. We use that a lot when we integrate. Log base a of x is 1 over x ln a. Again, doesn't come up a ton, but it could. Sine inverse, 1 over the square root of 1 minus x squared. And tan inverse is 1 over 1 plus x squared. Now, the way I remember this is sine, think s, think square root, think subtract. So sine has the square root and the subtraction. All of those start with the s. Tangent, think t, that looks like a plus sign, right? And there's no square root there because there's no s. So those are kind of how I keep those differentiated in my mind. You don't have to have all the other ones memorized. You could derive them if you need them. But again, on AB questions, we're really looking at sine and tangent as the ones that pop up the most. I guarantee you will see those. So please make sure that you know your inverse trig derivatives. So these are our methods of anti-differentiation, and these are sort of the ones that you're going to need to be most familiar with, and when do we use those. On your review sheet number 3, you'll notice that there's a place where it says, like, summarize the patterns that you see. Well, that just means, like, summarize for yourself when do you use which, and I'll give you guys some hints to that right now, and then we're going to do a bunch of examples. So, basic integration. Basic integration is when you see an integral that you know, okay? So basically, when you see a function whose derivative you know. So you know it's the derivative of another function. Now, this isn't always super clear to us. Sometimes we need to do a little work, but we know this is the derivative of something, of blank, okay? This is when this is really key. Always check if you can algebraically simplify first. So we're going to see some of those here below. So if I'm looking at especially these first two, I see this first one and I see that this can be algebraically simplified. So if I simplify this, I'm going to divide each of these by x. This would be 2x to the 4th. Now this thing right here, remember that this is x to the 1/3. So if I subtract 1 from that, because that's x to the 1st, this is going to be x to the negative 2/3 dx. And now each of these are just a power rule integral. So I can say, okay, well, derivative of 2x to the 4th, or 2x to the 4th is the derivative. So the 2 I'll just let hang out. X to the 4th go up a power, and then I'm going to multiply by 1/5. And I can just simplify that down, which would be 2/5 x to the 5th. Then my next one, so I'm going to just copy my minus there. I see that this is to the negative 2/3, so I'm going to go up a power, right? Add 1. So this is going to be x to the 1/3, and I need that 1/3 to cancel out, so there needs to be a 3 out front to make that cancel. And whenever I take that antiderivative, I want to put a plus c at the end because this is an indefinite integral. It's just a basic antiderivative. We don't know the initial value, so we need that c. So this is going to be 3x to the 1/3 and then plus c. So this is my final antiderivative. Now, you can check yourself, right? You can always check yourself by actually just taking the derivative of that. So let's try. Taking the derivative of this, the 5 would come down to the front. So I would get 2x to the 4th. Here, the 1/3 would come down, so it would be minus 1 x to the negative 2/3, and the derivative of any constant is 0. So I see that I get back what I started with. So, basic antidifferentiation. Again, there's another one that we could look at, which would be like this. So I've got 1 over cos squared, and your brain might go, oh my gosh, this is a u sub. I see it's 1 over cos squared. I can make u cos. It would be 1 over u squared. Sure. But do you see the derivative of cosine in there? Because I don't. So this is when, stop yourself before you get to u sub happy. Cosine squared, 1 over cosine squared, is really the same as secant squared. So this is the integral of secant squared. And now, I know that secant squared is the derivative of a function that I know. Secant squared is the derivative of tangent. So this would just be tangent x plus c. And you're done. So, again, always see if there's some algebra you can do first. Is it an antiderivative you know? Check. If not, okay, then there's something else we need to do. But if it's an integral we know it's the derivative of blank, then that's going to be when we just go and use basic antiderivatives. Okay? Again, feel free to send questions as we're working. If there's something that you don't get, ask about it. Next thing we're going to look at is when to do a u sub. So, u substitution. The thing that you are looking for is, first of all, you're looking for function composition. Because this is when we undo the chain rule. So function composition is the chain rule, right? That's when we would use it. A function in a function. The next thing I'm looking for with u substitution is I see, that's not how you spell C, I see a multiple of the derivative of u in my expression. Because I need u and I also need du. Okay, I have a whole video on my teacher site of how to do u substitution. using kind of a more algebraic way that will always work versus the more intuitive way that we do in class a lot. I'm totally happy with either way that you do, as long as you make sure that you know how to do it. So if you need that video, please go back to it. So I'm going to take a look at this and look at this one first. So I see that this is the integral of sine radical x over radical x dx. I know that some of us had a tendency to say, oh, it's always the thing in the bottom. But I don't know that. So sometimes you might need to use some trial and error on your u. I'm going to look at this and say, I see function composition. I see a function in a function. So that's what I'm going to test as my first u. So I see that this radical x is inside of that function. And so I'm going to test that as my first u. So u here would be radical x, right? Du then would be 1 over 2 radical x dx. And if that's not a derivative that you're familiar with at this point, get familiar with it. I know that you guys could bring down the 1/2, subtract 1, but you need to start getting more intuitive with the fact that when you see 1 over a radical, that probably comes from being the derivative of a radical. So just keep that in mind. So seeing this, I see that this is really the same as, I'm going to rewrite this integral a little bit, the integral of sine radical x times 1 over radical x dx. You don't have to break it up that way. I'm just doing it if people want to see that. And so I see that these two are related to each other. Now this is 1 over radical x. That one is 1 over 2 radical x. So I'm actually going to multiply both sides here by 2. So 2 du is 1 over radical x dx. If you were doing this the other way, you would solve for dx and then plug in. I'm again doing it the more intuitive way that you would see a college professor do it, but you can do it whatever way, okay? So this is going to be 2 times the integral of sine u du, once you simplify it down a little bit. And now I'm just integrating. The 2 is a constant. It hangs out in the front. What is the integral of sine? So what has an integral of sine? The integral of sine is the derivative of, well, it's not cosine. Derivative of cos is negative sine. So it would be the derivative of negative cosine. So the integral of sine is negative cosine. So this is what my integral looks like in terms of c. So what I really need to do now is plug my u back in. So negative 2 cosine of square root x plus c. Again, check yourself. Check yourself before you wreck yourself every time with these. So take the derivative of it. So the negative 2 would just hang out. Take the derivative of the outside, so that would be negative sine radical x, leave the inside alone, times the derivative of the inside, which would be 1 over 2 radical x, derivative of constant 0, so your 2's cancel, your negatives cancel each other out, and so this just equals sine radical x over radical x. So you see you get the same thing out. The one thing I would caution you here is don't get cancel happy. Okay, don't look at this and go, oh my gosh, there's square root x's, cancel, cancel. No, it's sine of square root x. You can't cancel out within the argument. So please make sure that you aren't doing that. Okay. All right, so let's look at another one. So if I look at this one right here, I see that I have 1 over x squared plus 2x plus 1. Some of you might be going, ooh, good candidate for completing the square, right? There's a problem with that. We'll see what that is in a second. There's a problem with u sub 2 here, if you just go straight into u sub. So straight into u sub, I would say u might be x squared plus 2x plus 1. It's in the denominator. That would make my du 2x plus 2. I don't see a multiple of that in there, so that's a problem. So this is where we're going to go back to this tip here. Always check that you can algebraically simplify first. Check it, right? See what happens. So let's say I do that. I would have the integral of 1 over, well, I can at least factor the denominator, right? This is x plus 1 times x plus 1 or x plus 1 quantity squared. So here's why trying to complete the square here might get you into a little trouble. The square is already complete. It doesn't really get you anywhere because you already have a completed square. So now when I look at this, why is this a great candidate for u substitution? Well, first of all, I see a function in a function. Right? I see composition. So that's my start. Second of all, I see that this is x plus 1, and the derivative of that is just 1. So that helps me out. So now I can do a u sub here. So u would be x plus 1. Du would be 1 dx. Now I can substitute in. So this is the integral of 1 over u squared du. And this is, again, where we get a little bit overexcited. We make some silly mistakes. A lot of people here will tell me this is ln of u squared because we're used to, when it's 1 over something, doing ln. But this is actually the integral of u to the negative second. And so what I need to do is think about that via power rule. So I need to go up a power. So adding 1 to negative 2 would be negative 1. I want that negative to cancel, so I'm going to throw a negative out front, plus c. So that is my antiderivative, right? Now that is not your final answer because you want it in terms of u, or in terms of x. So it would be negative x plus 1 to the negative first plus c. And that would be your final antiderivative. Now you could rewrite that a bunch of different ways. It could be negative 1 over x plus 1 plus c, right? If this was a multiple choice, there could be more than one way to look at this, but at least for this, any of those forms are fine. Again, send questions in as you have them. I'm happy to answer anything. Okay, so those are kind of my basic types, and now we're going to look into the two more algebraic ways of integrating. They are not other methods calculus-wise. It's u substitution, but from a calculus perspective, you need to be able to do the pre-calc, right? So that's what we're going to make sure. So when am I going to use completing the square? Completing the square, typically, what you're looking at is something in the form of a constant over a quadratic. 98% of the time, that's what the form will look like. Because the constant you can just pull out to the front, and so that would make it a constant, which I can't spell, times 1 over a quadratic, right? And quadratics are what we typically complete the square on. So that's what I would work with there. So I'm going to scroll down to some. We'll do those, and then we'll come back to some division. All right. So on this one, I see that I have a constant over a quadratic. Always check if it's factorable first, because it may be a scenario like the one we just did, where it's just a simple factoring trick. So this one, x squared plus 2x plus 2, I can't think of any integers that would add to be 2 and multiply to be 2. So I'm going to try completing the square. So I usually do that off to the side. X squared plus 2x plus 2. Completing the square, I'm going to cut my, well, first of all, I'm going to group this. I always leave a blank there, and I put the plus 2 on the end. And when I complete the square, I actually draw a little square just to remember what I'm doing. So half of this is 1. Square that, it's 1. So I'm going to add 1 in there. That's my completed square. Now, if I add 1, I also need to subtract 1 to keep that balanced. And then factor this. And this will always factor to be the same. It will always, I don't want that color, factor to be this variable and that number squared. So x plus 1, quantity squared, plus, combine your like terms over here, 1. And remember that that could be rewritten as this, right? That's going to be helpful for me because this is going to help me recognize what my antiderivative might be. So this is going to be the integral of 4 over 1 plus x plus 1 quantity squared dx. Now, why did that help me? Well, this is a really good candidate for a u sub now because I see this, the derivative of that is 1, and I have a multiple of that in my numerator, right? I have 4. So u is x plus 1, du is 1 dx, and so this would be the integral of 4 times 1 plus u squared du, or I'll bring the 4 out to the front, integral of 1 over 1 plus u squared du. Think about your derivatives now. What has a derivative of that? This is one you should know cold. Looking back up at our derivatives, that is the derivative of arctan, right? Tangent inverse. So this is going to be arctan of u plus c. You could also just say tangent inverse. And plug your u back in. So this would be arctan of u plus 1, x plus 1, thank you, plus c. Thank you to whoever corrected me on that. Perfect. That would be my final antiderivative. Okay, the last type we're going to talk about is when we need to do some division. And here's what I want to look at. When I look at this, I know that this looks like, oh, I see an x squared, I see an x to the first, right? But just think about this for a second. I've got x squared, I've got this. So if I made my u x squared plus 3x, and again, I wouldn't write this down, I'm just showing you what I mean. Du would be 2x plus 3. First of all, those are not multiples of each other, so problem. Even if they were, think about how we'd sub this in. This would be u, it'd be like over du. We don't want that. We never want du in our denominator. We always want du in our numerator because that's telling us like with respect to u, right? So when I see that, I see it's not a great candidate for u sub. I see that the top has a higher power. It doesn't have to. It could have the same power. But anytime I see that, that's a good candidate for division. So polynomial division, I'm going to look at this when my degree of my numerator is greater than or equal to the degree of the denominator. Those are really the key times that I look at it, denominator. Okay? Again, not the most common method that we use, but it can help. So I'm going to scroll down to this one. So I see here my degree of my numerator is 2. My degree of my denominator is 1. This makes this a good candidate, right? So I'm going to start with doing some long division. So x squared plus 3x plus 7. This would actually be a good candidate for synthetic division if you wanted to do that because the 0 is just 1. But I'm going to do it with long division as a review. So x times what would give me x squared? That would be x. Bring these down, multiply by each term. So x times x is x squared. X times negative 1 is negative x. And then you're subtracting this whole quantity. So you're going to subtract x squared, that's 0. You're actually going to add x here, so that's going to be 4. And then bring down your 7. And then I'm going to say, okay, x goes into 4x. That would be 4 times. Multiply those. So this would be 4x and then minus 4. You are subtracting the entire quantity. So you're actually going to be adding 4. So your remainder here would be 11. So this is x plus 4 plus 11 over x minus 1. And then that's what we're going to integrate. So we're going to integrate x plus 4 plus 11 over x minus 1 dx. And now all this is basic integration with a little teeny bit of u sub. So basic integration, integral of x is x squared over 2, right? Integral of 4 is 4x. Integral of this quantity right here. You can do a u sub here. I actually think a lot of us are to a point where we could do this in our head. But u here would be x minus 1. Du would just be dx. And so this would be 11 times 1 over u du. And so that just becomes 11 times ln absolute value of u, which is x minus 1 plus c. So that is my form for long division. So again, this summary will kind of help you with that last page of your review number 3. These are all what I look for when I do these. But again, if you see other tips or tricks that help you, add them in, share them with your class. Those are great resources. So we have about a half hour left, 35-ish minutes. So I'm going to do a couple basic separation of separable differential equations, and then we'll do some applications and some questions that you guys have sent in. If you haven't already sent in your questions on review 1 and 2, send them, please. I want to do the stuff that you guys struggle with, not just babble at you. So I'm going to start with these. I'm going to hit a couple big topics, including what's the deal with the plus or minus? What's the deal with the C thing? What are my laws of exponents that I might want to use here? So let's keep those in mind. So here's the big thing with separable. You want everything with a y on one side with your dy. You want everything with an x on the other side with your dx. And notice, they need to be multiplied together. So you need this to be a product. And you need your dy and your dx in the numerator. So you never want to have it in a form that's like 1 over x dx. Not cute. We would then need to move that dx over to the other side so it would move to the numerator. So keep that in mind. That's going to be really important, okay? So, again, break it up into a product of x's and y's. So, we're going to start by finding the general solution, and then we'll move into finding the particular solution. So, finding the general solution, we're going to try to get this separable. And Leah, I see your question. We will definitely do one with a tangent line in a second. Great question. So, I'm going to separate this into y's and dx's. If you can, cross multiply. That's the easiest way to do this. So, if you can, I'm going to put the y's with the y's, so multiply those, x with the x's. So, I would have y dy is 2x dx. Again, no calculus yet, just separation. The calculus comes in this step, and this is the only calculus you do in these, which is to separate it and say, okay, integral of y with respect to y is y squared over 2. You can put a plus c on that side, but you don't need it. You only need it on one side. The other side, this integral would be x squared. You don't need the over 2 because of the 2 out front. And I'm just going to put my plus c here. So there's my general antiderivative. The calculus you do here is done now. To find the general antiderivative in the form we normally want it solved for y. So I'm going to multiply through by 2. So 2x squared. Now, 2 times c is still a constant. So let's say you call that c1. Maybe this is c2, right? Or just c. So that's totally fine there. Square root both sides. So then you would get y equals, and this is important here, in your general antiderivative, you need the plus or minus, so it would be 2x squared plus c. So this is my general antiderivative. General means it's the family of solutions, it's the family of curves, and so you're still going to have your c there. So I'm going to do one particular solution to make sure we're okay on that. So this one says, find the particular solution that goes through 0, -5. Okay, so let's do that. I know this is my general solution, so I'm going to bring that over. So y equals, so -5 equals. Now, it says plus or minus, but I see that my output here is negative. So I know that it's going to be minus the square root of 2x squared plus c. So 2 times 0 squared plus c. And again, I knew that this was negative because your y is negative. Right? I don't need the is there. Y is less than 0. And so that only happens in a square root when your coefficient out front is negative. So solving this, I'd square both sides. 25 equals c. So your particular solution here would be y equals negative, not plus or minus anymore. You know it's negative. Square root of 2x squared plus 25. And that is the particular solution. So you can drop the plus or minus when either you find the particular solution and know it's plus or minus, which is this case, right? Or you rewrite an expression algebraically in a way that accounts for the plus or minus. So let's say we have something like this. Absolute value of y equals e to the x squared plus c. So I would add in a plus or minus here because I'm taking away the absolute value. So that's where it comes from. But when I rewrite this, remember that this is e to the x squared times e to the c. And this is a constant. Constants can be positive or negative. So I don't need that plus or minus out front anymore because that c accounts for the plus or minus. So that is another case where you can drop the plus or minus. Okay. So let's do some more separation. If you have questions about the plus or minus, send them, but I'm going to do a couple more weird separation ones, okay? So this one, dy dx is 1 over secant squared y. I see this is with a y, so I need to move it, right? So this is going to be secant squared y dy equals 1 dx. I'm going to integrate both sides with respect to their respective variables. Integral of secant squared is tangent y. Again, gotta know it. Equals integral of 1 with respect to x is x plus c. Now, that is calculus. Done. How do I get that in the form that I want, which is solved for y? So the thing you have to think about here is to get y out of this, the only thing you can do is tangent inverse. So this is going to be y equals arctan, or tan inverse, same thing, of this whole side. If you knew the particular solution or you knew an initial condition, you could plug it in to get C. I don't, so I'm just leaving C there. Okay, next one, get a little tougher. So I've got dy dx is 2y plus x plus yx squared. Does not look separable right now, right? Remember, you want products, not sums. So before I cross multiply, I'm going to try to at least separate my x's and y's. So dy dx is going to equal, factor out your greatest common factor here, which is a y, 2x plus x squared. Now at least I see that I have products, so this may be separable. So I'm going to move the y over. So 1 over y dy equals 2x plus x squared dx. And I'm just going to combine those. And I'm going to integrate. So now we're actually going to do a little calculus. So this is ln, absolute value of y, equals, integrate each of these individually, x squared plus x cubed over 3 plus c. Again, calculus, done now. Now all I'm doing is the pre-calc to get y alone. So in that case, what I'm going to do, I have ln, I want y alone, so I'm going to make e my base of both sides. So this will be absolute value of y equals e to the x squared plus x cubed over 3 plus c. Same trick that we used up here, right? I know that when I'm adding exponents, it means the bases were multiplied. So absolute value of y, or actually let's drop that. Let's put some plus or minuses in. E to the x squared. I know I could do times e to the x cubed over 3, but that doesn't really make it simpler. Times e to the c. So this is still a constant. So since that constant could be positive or negative, I'm going to drop the plus or minus. C e to the x squared plus x cubed over 3. It is totally not wrong if you didn't drop the plus or minus there. But let's say this was a multiple choice and you had to match it up with an answer choice, the plus or minus won't be there. So that's why we continually show you that. Ms. Belton and I are doing that a lot. So make sure that you're seeing that that can go away. Okay. Good. All right. Next one. This one looks kind of ugly. Means it's going to be my favorite type. So next one, I've got dy dx is e to the x minus y. And right now, does that look separable? Probably not, right? That does not look like a product. So I need to go back to pre-calc. No calculus yet in this one. I need to make that separable somehow. So I'm going to have dy dx equals, I see that I'm subtracting my exponents. So if you know my stupid dances, divide, subtract, right? Divide, subtract. So if your exponents are being subtracted, it means that your same bases were being divided. So I can do that. So now this is separable. So now I've got, okay, e to the y dy equals e to the x dx. And I can integrate. So integrate both sides with respect to their respective variables. Everyone's favorite integral of e to the y is e to the y. Integral of e to the x is e to the x plus c. I'm looking at you if you didn't write it on your last quiz. And calculus is done. So all you need to do now is you need to make sure that you're solved for y, right? Get it into the form you want. So what I'm going to do here is I'm going to actually take the natural log of both sides and make sure you do it to the entire side. So this would just be y. And then this would be ln of e to the x plus c. Again, if I had an initial condition, I could solve it, but I don't, so I'm leaving it like that. Okay, last one of these, and then I'm going to take your questions. A couple of people have sent them. Keep sending them either through Remind or the live chat if you haven't. But this one looks pretty separable, right? This is all in terms of x. That's all in terms of y. So let's get started with this one. So I'm going to bring the dx up there, bring the e to the y over to here. So I get 1 over e to the y dy equals x dx. So, separated, integrate, the only calculus we do here. And let's start on the right side, because I actually think you guys are going to be much better at that. Integral of x is x squared over 2 plus c. This left side gets a little iffy for me. A lot of people here are just going to tell me it's ln of e to the y. It is not. That is not just ln. Every time you see 1 over does not mean it's ln. ln is 1 over something to the first. This is not that. So I'm going to actually rewrite this as the integral of e to the negative y dy. And I know that looks eerily like one of the antiderivatives we know, but it is not. The one that we actually know, I'm going to scroll back up, is just e to the y. We don't know e to the negative y. So what that means is that I'm going to actually need to do a u sub here. So sometimes we get lucky and we get to do u subs in separable differential equations. Valentine's Day is coming up, so this question could be your Valentine. I don't know. So I'm going to make this my u. So I'm going to make du negative 1 dy. Because remember, this is in terms of y. So that's what I want it to be. And then this is going to be the integral of e to the u du, and you need the negative 1 out front. So here I get, let me go back to red, negative e to the u, which was negative y, equals x squared over 2 plus c. So again, sometimes you get lucky. So now I need to solve for y. So this would be multiplied by negative 1 on both sides. So e to the negative y is negative x squared over 2. Again, you can make this minus c, but it's still a constant, so leaving it as plus c isn't a problem. Now I'm going to take the natural log of both sides, sticking with our Valentine's Day colors here. Okay, so this is going to be negative y equals ln of negative x squared over 2 plus c. And then solve for y. So y is the opposite of the natural log of negative x squared over 2 plus c. And there would be some domain restrictions here based on what your c value is, because you don't want this to come out to be negative, right? So we'd have to be careful with that, but they didn't ask for a particular solution, so it's okay on this one. Okay, so the first question I got from a lovely viewer is about tangent lines. So I'm going to scroll through this really quick and see if there's one where we had to do that. So, so this is on review number 2. No, this is still on review 1. And it is this question right here that says, consider the differential equation dy dx is 3, or y times 3x squared minus 1. So to start off, we've got A, B, and C. This would be a 9-point free response. And starting with a slope field, you're like, thank heavens that I got a slope field. Just plug in your points, right? So for the slope field, I'll do this with you guys. We're just going to plug in our points. So if I plug in, and again, feel free to make a table of values if it helps you to stay organized. I get very jumbled when I make these if I don't stay organized. So I know that I have negative 1, 0. I have 0, 0. I have 1, 0. I have negative 1, 1, 0, 1, 1, 1. Keep going like that. So when you plug in those values, anywhere that y is 0, this is going to be 0. So all of these values here, it's 0. So that helps. That'll be an isocline, right? So my slope at each of those would be 0. So that's my isocline for 0. Then you can start plugging in your other values. So this one would be 1 times 3 minus 1, right? 1 times 2. So that's 2. So at negative 1, 1, my slope would be 2. And again, you're estimating. So up 2 over 1 would have a slope maybe like that. Okay. Then plug in 0, 1. So 1 times negative 1, this would have a slope of negative 1. So going downhill, that kind of slope. 1, 1, I would have 1 times positive 2. Again, so this would be a slope of positive 2. So parallel to my original slope. Okay, keep going like that. I'm not going to finish all of these right now because I have faith that we could probably, find the rest of the values. So part B says, let f of x be a particular solution. Notice, it does not say in part B to find the particular solution. A lot of people will go very wrong on this because they do all this work that they don't need to do, and they don't get the points because they don't answer it. So it says assume it is. Okay, cool. I'm assuming it is. At the initial condition, y of 1 is 1. So I always think, hey, that's a point. Just keep that in the back of your mind. Write an equation for the tangent line at 1, 1, and use it to approximate f of 1.1. So let's start with the tangent line. You need a point, you need a slope. So the point I know is going to be 1, 1, right? The slope, well, that's going to be dy dx at 1, 1. So dy dx is going to equal at 1, 1. I said it was 1 times 2, which would be 2. So the equation of my tangent line would be y minus 1 is 2 times x minus 1. And so that's the first part. Find the equation of the tangent line. Done. Use that to approximate f of 1.1. So now I'm going to plug this into my tangent line. So y minus 1 equals 2 times 1.1 minus 1 is just 0.1, or 1/10, right? So this is 1/5, 2 times 1/10. And so it would be y equals 1.2 or 1/5. Either way, this would be your answer to part B. Okay? And then let's say they asked us to do part C. So part C says, find the particular solution. So now I actually want to find it, right? Plug it in, find it. So this is separable, which FYI, it's the only method you learn in AB, so they should all be separable. So I'm going to separate it. So it would be 1 over y dy equals 3x squared minus 1 dx. And I'm going to zoom in on that so we can see it a little better. Let me shrink it down. Okay, so ln, absolute value of y, equals 3x squared. Well, that would just be x cubed minus x plus c. So that's the calculus and this done. Now, because I have ln, I'm going to do e as a base on both sides. So this will be absolute value of y equals e to the x cubed minus x plus c. And again, I can put the plus or minus there. So y equals plus or minus e to the x cubed minus x, and I'm going to make that e to the c. So writing that in this form, I'd get c e to the x cubed minus x. That is my general solution. They want the particular solution at 1, 1. So 1 equals c e to the 1 cubed minus 1. So I get here that c equals 1. So my particular solution is 1, which you don't have to write, but you can, e to the x cubed minus x. Okay. So we've got about 15 more minutes that I can stay on. If nobody has any other questions, I don't have to stay on. But do we have more questions? Look through your review 1 and 2. See if you have more questions on that. Again, we're not going to go over those in class, but what I'll do for Tuesday is tomorrow in class, I will give you the paper that we're going to go over, because a lot of you guys, your feedback last time said it'd be helpful to have the paper, and then I'll go over any other questions you have on this then too. But I'll give you guys 2 minutes, send me any last questions, and in the meantime, I'm just going to sit here, strangely, and wait for your questions. Yes, I did chop all my hair off, by the way. Okay, I see a question. Let's see. So we have, do you have to write plus or minus for the particular solution in part C? The one we just did. So let me scroll back to that. So that's a great question, and this comes up a lot with people, like when do you need the plus or minus and when do you not? So first of all, for a particular solution, you will never need the plus or minus, because a particular solution will either be plus or it will be minus. So you don't ever need it for a particular. For the general solution, I did drop the plus or minus. So let me go back to why I did that. So let's look at this one. I don't need it there because I solved for C. C was positive, so I don't need the plus or minus. The reason that I dropped it right here is because in this step above I had it, right? But then I said that this e to the c was actually just a constant. And constants can be positive or negative. So let me show you the intermediate step I did here. This could also be y equals plus or minus c e to the x cubed minus x. Right? That's correct. That wouldn't be wrong. But what I did was I said this is still a constant, right? Plus or minus. So that's why I dropped it there. I said this would be c e to the x cubed minus x. And then you don't need the plus or minus because that c kind of takes it into account. So when I said earlier, like do an algebraic simplification that takes that into account, that's what I meant by that. Hopefully that answers your question. And if it didn't, send it, rephrase it, say, but I still don't understand, whatever. Okay. What else? Good. I'm glad that answered it. In class, my plan is to just do tons of applications practice. So we're going to solve the murder mystery. Obviously, we got to find out who did it. And then we're going to do a bunch of applications practice. Okay, somebody said finding an equation for a curve. Can you give me an example? Normally, find the equation for the curve would just be another way to say find a particular solution. So let me see if I can find an equation or an example of that in here. Otherwise, just send me an example. Because again, that's like rephrasing it a different way. So maybe this one says the curve has a slope of x minus 2 at each point xy on the curve. What's the equation of the curve? This one's really funky, the way they say this. So we got to do some decoding. So let me know if this is the one you're asking about. But I'll start this one, and if it's not, we'll do the other one too. So curve has a slope. That should automatically make you think derivative, okay? So what this is saying is dy dx is negative x plus 2. It wants the equation of the curve. That's saying find y, right? So find the particular solution there. So this one actually isn't even separable. You don't even need to know, like, to separate it because there's no y. So you can separate it, but you could also just do a basic integral. So let's say you want to separate it. So 1 dy is negative x plus 2 dx. I'm going to integrate both sides with respect to x, and that's going to give me y equals negative x squared over 2 plus 2x plus c. So now I need to find my c value, but I already can kind of tell which one it's going to be. But to find c, they told me it goes through 2, 1. So I'm going to plug that in. So I know 1 would equal negative 4 over 2 plus 4 plus c, right? So 1 is negative 2 plus 4, so 2 plus c, so c should be negative 1. And so I know that it has to be c. So just saying find the particular solution. All right, somebody else just asked how many free response and multiple choice. To tell you the truth, off the top of my head, I don't remember. So I'm going to go behind the scenes here, ignore all the clicking. I'm going to open it up and I'm going to tell you. My best recollection is that there are 7 multiple choice, I want to say. And then the free response range in type from very straightforward, very simple, just take an antiderivative, to, you know, AP style, like ABCs, like the one that we just went over. Okay, I'm opening it now. You can't see it. It's in the background. So multiple choice. Yep, we've got 7. And they range on topics, slope fields to all this other stuff. Then there are some basic antiderivatives and a couple application problems. So total, you've got, it's only a 15 question test. So 7 multiple choice and 8 free response. Some of which have ABC. Okay, anything else? Kudos to those of you that have hung in there this whole time on your Sunday afternoon. You guys are awesome. Let me see if I can see any others. Be able to draw a slope field. Definitely be able to match slope fields. Be able to separate. Be able to figure out when to use PERT, right? We did that in last class. We'll go over this review in my class tomorrow. Anything else? Okay. I'm super proud of you guys. Thanks for hanging in there. And you only have 2 calculus tests left after this. Maybe 1 if Miss Belden and I are feeling nice. So we're going to start getting into some more heavy review. But I'll be back Tuesday night, 7 o'clock. And again, this will all be available live or archived on my website if you need it. Yes, I will put the keys for review 1 and 2 on my site. And review 3, I'll give you guys the keys in class tomorrow after I check it. Okay, I hope you have a great Sunday. And I'm going to go grocery shop now so that I have lunch. All right, I'll talk to you guys later. I'll see you tomorrow.